Dear friend, I have come with a very interesting example for the calculation of deflection at a point B for a cantilever beam which is subjected with a uniformly distributed load W. Length of this beam is L and the deflected shape of this beam is this one, deflected curve, deflected. And our objective is to find out delta B. Now problem statement is calculate deflection at tip of a cantilever beam. This is the tip of the cantilever beam which is subjected with a uniformly distributed load W throughout its length. In this problem we are going to find out deflection delta B using conjugate beam method. This is the lecture 4 and in my previous lecture 2 I have solved same example using unit load method for which I want to show you some preview. Unit load method problem statement same. It is a cantilever beam having length L subjected with UDL W and we found out delta B, and value calculated for the deflection delta B is, this is delta B, value is WL to the power 4 divided by ATI. You can go through this lecture to enhance your knowledge now. In lecture 3 you will find same example which I have detailed with another method that is called the moment area method. Example is same. Span of the length of this beam is L subjected with UDL W, and we have calculated delta B for this beam, and it was solved with moment distribution method, moment area method. Now you can see preview for this lecture. We have solved something like this. I have generated M over EI diagram, centroid something, then we calculate the value delta B as WL to the 4 divided by ATI. The value calculated from the moment area method and unit load method is same, WL to the 4 divided by ATI. Now in this session, in this lecture 4, I am going to solve same problem using conjugate beam method. Before starting this lecture, I want to explain something regarding how the conjugate beam is developed, and you can say how the real beam is converted into a conjugate beam. Suppose this is a real beam, length L, having fixed support this, and free end is B and fixed end is A. Its corresponding conjugate beam will be free when free end will become a fixed support. This is a free end, this is a free end, it will become a fixed support, and fixed end of a real beam will be a free end. This is a free, it will become a free end. It is a real beam and this is a conjugate beam. Conjugate beam. For real beam, if it is subjected with a load, suppose this is a load, maybe UDL, point load, triangular loading or trapezoidal loading, it will have a deflected shape. This is a deflected shape, and according to the conjugate beam method, if we are able to find out bending moment at this point B, then it will, MB, bending moment at B, will directly give this is delta B. MB equal to delta B. Anywhere, if suppose you are able to find out bending moment at this point, then at the same point it will give a deflections for the real beam. So first we will convert this beam as a conjugate beam, then we will find out bending moment at this point for a conjugate beam. You can say bending moment at B, bending moment at B of conjugate beam will give deflection at the same point in real beam. You can say in the same corresponding real beam, in the same point in corresponding real beam. Now first we have to convert a real beam into a conjugate beam. Now our problem statement is, this is the problem statement. This is a cantilever beam subjected with UDL W. Length of this beam is L. This is the real beam. Now its conjugate beam will be, as I have explained you, this is point A, this is point B, and fixed end will become a free end. It will be a free end, and free end will become a fixed end. Now point A and B will be same, length will be same L, but it will be a conjugate beam. Now in order to find bending moment at this point, so that we can directly find delta B here, we need to develop a loading diagram on the conjugate beam. Now as per the theorem of conjugate beam, it states that the M over EI diagram, M over a bending moment over EI diagram for a real beam will be directly put on the conjugate beam to make its loading diagram. So try to understand this concept. This is the real beam. Real beam is this one. I am showing you in a large view. This is the real beam. Length is L. This point is A. This point is B. We are taking a section XX to find what a bending moment diagram. This section XX at a distance of B, at a distance X from point B. So general bending moment will be MXX. Yeah, MXX will be, this is the W, and our assumption is anticlockwise bending moment will be negative. So this is W, it is UDL in kilonewton per meter. Loading UDL multiplying with distance X will give a total load, and this load will be acting at a length of X by 2 from section X by 2 at a distance of X by 2 from section XX, and this will be the load. Load will be W into X. W multiplying with this length will give total load. The total load for length X. So, and this Wx, which will be converted as a point load, will be acting at a distance of x by 2 from section xx. So moment will be this Wx multiplying with distance x by 2, load multiplying with distance is nothing but moment, and as this moment is in anticlockwise direction, so moment will be minus sign multiplying with the Wx, and length is x by 2. It will give minus Wx square by 2. This is a general bending moment, but it is in parabolic nature. So that we can draw a bending moment diagram, parabolic nature. Now, at the general section xx, we have found bending moment mxx is minus Wx square by 2. In order to find bending moment at A, that will MA will be what? In place of x, if we put x equal to L, if x equal to L, it means at a length of L from this point B, bending moment MA will be minus W by 2. In place of x, we put value L, it will be square of this L minus WL square by 2 will be bending moment at point A. At support, bending moment will be WL square by 2. So bending moment curve will be BMD will be, this is a bending moment curve having a parabolic nature, so we will draw bending moment curve is in this manner, and its value will be WL square by 2. It's a support moment, so it will have a negative sign. Length is same. This point is A and this point is B. This is the M diagram, or you can say that it's a bending moment diagram for real beam. Now we have to convert this real beam into a M over EI diagram. Now I am going to draw M over EI diagram for bending moment diagram of a real beam. As I have shown, this is the M diagram, and I am drawing the same M diagram. This is the M diagram. Bending moment profile is this one. Length is L, and maximum value is WL square by 2. Maximum value is WL square by 2. And this point is A. This point is B. This is the M diagram. Corresponding M over EI diagram, M diagram for real beam. Now, corresponding value of M over EI diagram will be, we are going to draw M over EI diagram. M over EI diagram. M over EI diagram says every y coordinate of this M diagram, I mean bending moment diagram, every y coordinate will be divided by a constant value of EI. This is a constant value of flexural rigidity. It is constant is elasticity, I is moment of inertia, and its value is constant for any structural member. So we are going to divide all the y coordinate divided by constant value. So the profile will be same, bending moment curve will be same. It will be a function of x square, that will be a parabolic that I have shown here. It's a parabolic in nature, Wx square by 2. The profile will be same, but value will be somehow lesser than as compared to this one. Value will be this. This will be WL square divided by twice EI, because we have divided M divided by EI, so it will be WL square by twice EI. This is the M over EI diagram. Okay, fine. Now, as per the statement of deflection calculation using using conjugate beam method, it states that to develop a loading diagram in a conjugate beam, we need to put M over EI diagram directly on this beam in the same as it is shown here. So loading diagram in a conjugate beam will be the point is same, it's A, it's B, and it will be directly put on the conjugate beam. This beam, conjugate beam is this is the fixed support and this is a free support, and free support is A, free end is A and fixed support is B, and our M over EI diagram is in this fashion. This is the profile of this M over EI diagram. It will be put directly on this beam, and it will be loading will be in this profile. It will make a loading diagram on a conjugate beam. Now our main focus is to find out bending moment MB, any bending moment at point B, bending moment at point B of this M over EI diagram, M over EI diagram of conjugate beam. Now this is the conjugate beam with loading profile, conjugate beam with loading pattern. This is a cantilever beam having a load in this profile. The loading curve is a parabolic curve. Function of this curve will be x square. Now if the area of this loading diagram multiplying with the centroid will give directly bending moment at point B. So if we are able to find out MB, bending moment at B, it will directly give deflection at delta B. It will give directly deflection at delta B for real beam. Okay, now our main focus is to find out MB for a conjugate beam. Now we have developed conjugate beam having its loading pattern. Conjugate beam is this one, this is fixed, this is free end, and loading pattern is this is our loading pattern. Point will be A, it will be point B, and length is L. This value is WL square divided by twice EI that we have calculated here. WL square by twice EI, as we have converted M diagram to a M over EI diagram. M diagram converted to a M over EI diagram, and this value is WL square by twice EI. Now centroid of this beam will be, for bending moment we have to take the overall total loading will be acting at a distance at a point which will be the centroid of this loading, and its distance will be x bar. Total load will be acting here, the total load. total load, or you can say W capital. Yeah. Now total load will be the area of this loading diagram. Total load will be equal to area of loading. This is a conjugate beam with loading pattern, with loading pattern. Total load will be equal to area of this loading pattern now. This is the loading profile is a parabolic profile. So total load will be 1/3 multiplying with this base L multiplying with this height will give total area of this loading pattern, WL square divided by twice EI. It will be WL to the power cube divided by 6 EI. This is total load W. Now total load W is acting at a distance of x bar from point B. X bar is nothing but the centroid of this loading pattern. Total load will be acting at its centroid. So as we know, for a parabolic curve, x bar is 3/4 of this length L. We have calculated x bar and we have calculated total load. So moment at B will be load multiplying with this distance, centroidal distance will give moment at point B. Hence MB will be it will be in anticlockwise direction. That will be in anticlockwise direction moment. So MB will be total load W multiplying with x bar. W is WL cube divided by 6 EI multiplying with x bar. X bar is 3 divided by 4L. Now 3 divided by 6 will be 2 and its value will be WL to the power 4 divided by 8 EI. This is the value calculated for MB. This is value calculated for MB, which is WL to the power 4 divided by 8 EI. Same value we have calculated using unit load method, conjugate and moment area method. Yeah, and you have to in our lecture third, I have also given you a general formula, general expression to find out centroid, x bar and area of any kind of curve which are having a function of x to the power n. Since the function x to the power n, I have given you general formula. Area will be 1 by n plus 1 multiplying with length into height. Suppose a curve is following, this is the curve, function of this is length L and this is height h. Suppose function is x to the power n, so area will be 1 divided by n plus 1 L into h, and x bar will be n plus 1 divided by n plus 2 into L. Here in this example, since the parabolic curve is a function of x square, so n will be equal to 2. So area will be 1 divided by n plus 1 now, 2 plus 1 into L into h. So area will be 1/3 of L into h that we have taken. This is h, this is h, this is L, and 1/3 of this length multiplying with this h, this is h. So we have calculated total load W from this formula, and x bar is n plus 1 divided by n plus 2. In place of n, we can put 2 plus 1 divided by 2 plus 2 into L. This is 3 divided by 4L x bar. I have directly used formula 3 by 4L. So we have calculated WL to the power 4 divided by 8EF, which is the bending moment at point B for a bending moment for a conjugate beam. This is bending moment for conjugate beam at point B, at point B. So as per the statement of conjugate beam theorem, the same bending moment will give the deflection at the same point for a real beam. So delta B will be deflection at point B, or you can say deflection at point B of a real beam. Deflection at point B of real beam, which is our subject of analysis. Delta B, deflection at point B of real beam, is nothing but MB, which is the bending moment for a conjugate beam at point B. I hope your concept might have cleared. Friend, keep watching and keep sharing to your friends and colleagues. And I hope your lecture, this lecture might have cleared your concept regarding the conjugate beam. And for any confusion, you can write in a comment box, and I will answer you. Thank you so much.